Hi guys, today we're going to do the lab for lesson 5 in your science fusion book. I sent an email out where you can do it by yourself online. If that doesn't work, however, you can watch this video and do it along with me in the video. So it's how can we model physical adaptations?
Welcome to the lesson, How Can We Model a Physical Adaptation? In this lesson, you're going to explore animal adaptations and learn how these adaptations help animals survive in their habitats. The hedgehog is a small animal. It's small enough to fit in your hands, but it's too prickly to hold. Its back and sides are covered with sharp spines. When the hedgehog rolls up into a ball, only its sharp spines can be seen. Do you think the hedgehog's spines and its behavior of rolling into a ball help it survive where it naturally lives? In what way? Type your answer in the box and then click OK.
So we learned that adaptations are things that animals can do that protect them and keep them safe. So I'm going to say that yes, the spines in rolling in a ball help the hedgehog survive. Because it helps, or let's say because the spines hurt to touch. T-O-U. And when it's in a ball, it looks like a pine cone or other plants to blend in. Because if we can't see its face, another animal might think that it is just part of the forest floor.
The hedgehog's spines and its behavior of rolling into a ball help protect it from its predators, such as the badger. The hedgehog's spines and its behavior of rolling into a ball are called adaptations. Click each image to learn more about adaptations. Start with the polar bear.
I don't think it worked yesterday, but we already know from when we learned about Antarctica and the Arctic, like the North Pole, because polar bears don't live in Antarctica, that the animals that live in cold places have extra fat, like the blubber on penguins. So the polar bears have that blubber to keep them warm, and they have their fur. And then we can see that it's white, so it matches the snow. And it has those big paws so that it doesn't fall into the snow, like it can walk on top of it, kind of like snowshoes. And then we'll see what else the video tells us about them.
Adaptations are features of living things that help them survive in their habitats. This polar bear's thick fur helps it stay warm and survive in its cold habitat. Did you ever think there could be so many different kinds of bird beaks? Could a bird beak be an adaptation? If so, for what?
So if we look, the first bird up here is a hummingbird, and it has a little pointed beak, and we learned about them when we were doing the life cycle, that they drink nectar from from flowers. So if they have this little small beak, it kind of looks like a straw, so it makes it really easy for them to suck the nectar out of the flowers. Then the bald eagle is a bird that eats like rats and different animals, so it has that pointy almost tooth on the front of its beak that helps it bite into the skin and eat an animal, whereas the duck underneath it doesn't need that pointy tooth almost on the front of his beak because he's not trying to eat any animals. He just eats mosquitoes and bugs and different things like fish that you don't need to have that pointy tooth on the front to eat. Same with the toucan. He has a big beak because he has to crack open nuts and berries. And he's more colorful because the places where he lives, they are a lot of the time they're by fruit trees. So his beak kind of blends in with different fruits that would be in the rainforest where he lives.
One way to explore adaptations is to use a computer model. A model helps imitate something that happens in nature and helps us ask, what if? In this lesson, you'll use a model to explore the adaptations of two imaginary creatures. The only difference between the creatures will be the size of their mouths. Let's call one the large-mouthed creature and the other the small-mouthed creature. The model you'll use in this lesson has two habitats for these creatures. In one habitat, there are only healthy bugs. In the other, there are healthy and poisonous bugs. Healthy bugs are blue. Poisonous bugs are red. In this lesson, we'll call poisonous bugs toxic bugs. In this lesson, the imaginary creatures want to eat as many healthy bugs and as few poisonous ones as they can. Will their mouth sizes make a difference in the two habitats? That's what you're going to investigate. Continue on to start your investigation. In this lesson, you'll investigate what happens when two creatures with different mouth sizes eat in two different habitats. Here's what you'll use. A model of creatures eating bugs. Two types of imaginary creatures. You'll use these two imaginary creatures. One has a large mouth. One has a small mouth. You'll choose one creature at a time to eat the bugs. Two habitats. Here's where you'll choose the two habitats with bugs. Remember, the healthy bugs are blue. The poisonous ones are red. On the screen, the poisonous bugs are called toxic bugs. A clock. The clock will show you how much time you have left in each session. Each session is 15 seconds. A data table. You'll record the number of healthy and poisonous bugs each creature eats.
Alright, so then the next page should be the experiment where we're going to test our hypothesis.
It's time for you to make a prediction. Will the mouth size of each creature help it survive in a particular habitat? What do you think? Click yes or no.
Okay, so there's two different options. So the first habitat, there's only good bugs. So do you think the largemouth one's going to be better or the smallmouth one's going to be better? Then think about them in the other habitat where there's good and bad bugs. So do you think the larger mouth's going to have an easier time eating the bugs or the smaller mouth one? So I'm going to say yes, the mouth size is going to help survive in different habitats. Remember, because it's a hypothesis, if you don't agree with me, that's okay, because this is a guess. We don't really know what's going to happen. So even if you think it's no, that doesn't mean you're wrong. It means you have a different guess than I do.
Soon you'll find out if your prediction is correct. Now you're going to make a plan to check your prediction. Show how you plan to carry out your investigation in each of the two habitats. Drag the steps in order.
So first I need to pick my creature. Then I need to eat the bugs. Write down how many bugs I ate, and then
Good work.
the other one.
Now you have a plan for your investigation.
Next
You're ready to see what happens when two creatures with different mouth sizes eat bugs in two different habitats. You'll start by testing the large-mouthed creature in each of these habitats. Click the large-mouthed creature button. Now click the Only Healthy Bugs Habitat button. To start the model, click the Run button. Start eating healthy blue bugs by clicking them.
They're all stuck up
The
here.
number of healthy bugs eaten in this habitat appears here. Enter this number in the data table in the row for the Only Healthy Bugs habitat.
So I ate 42 bugs.
Click the Reset button.
Reset.
Now click the Healthy and To start the model, click the Run button. Start eating the blue healthy bugs.
Oh, it's harder to click on only those ones and not get the other bugs. Ah! Yikes. Uh-oh, I ate a bad one. I don't see any other ones.
The numbers of healthy bugs and toxic bugs eaten in this habitat appear in the boxes above. Enter these two numbers in the data table.
So that time I only got 15 healthy bugs and I ate one toxic bug. It was a lot harder that
Click
time
the
because
Reset button.
I had to avoid clicking on the red ones and only click on the blue ones.
You're ready to test the smallmouth creature in these two habitats. Now click the smallmouth creature button. Now click the Only Healthy Bugs habitat button. To start the model, click the Run button. Start eating healthy blue bugs by clicking them. The number of healthy bugs eaten in this habitat appears here. Enter this number in the data table in the row for the Only Healthy Bugs habitat.
Okay.
Click the Reset button. Click the Healthy and Toxic Bugs habitat button. To start the model, click the Run button. Start eating the blue healthy bugs. The numbers of healthy bugs and toxic bugs eaten in this habitat appear in the boxes above.
Okay,
Enter these two numbers in the data table.
Alright, are you done talking? 5 healthy bugs, and I did not eat any toxic bugs that time. Next.
Look at your data. Compare how many healthy bugs the two creatures ate in each habitat. Compare how many toxic bugs the two creatures ate in each habitat. Based on your data, answer the questions. Drag the creatures to where they belong. When you're finished, click OK.
Alright, so the largemouth creature and the only healthy bugs ate 42, and the smallmouth creature ate 13. So the largemouth creature ate more healthy bugs. In the habitat with both healthy and toxic bug, which creature ate fewer toxic bugs? So the largemouth creature I ate one toxic bug, and the other one I didn't eat any.
Good job! Based on your results, is the following sentence true or false? The mouth size of each creature did not make a difference in the two habitats. Click true or false.
Did it make a difference? Did the largemouth creature do better both times, or only when there was only healthy bugs? So he ate more both times, but he did eat one of those toxic bugs, so it does make a difference. So that means the mouth size of each creature did not make a difference. It's false.
You got it! The mouth size of each creature made a difference in the two habitats. The large-mouthed creature is better adapted to the habitat with only healthy bugs because its big mouth helps it eat more healthy bugs than the small-mouthed creature. But the small-mouthed creature is better adapted to the habitat with both healthy and toxic bugs. Its small mouth allows it to eat the healthy bugs without eating the toxic ones at the same time. In the mixed habitat, it's much harder to avoid toxic bugs if you have a large mouth. Remember the bird beaks? Remember the bird beaks? Bird beaks are also adaptations. Different bird beaks are adapted for different food sources. Match each bird to what its beak does.
Alright, so opens nuts and seeds. Is that toucan? I think. Oh, wait. Okay, I gotta drag him down. Tears meat apart. Remember I said the eagle has the pointed, sharp tooth on the front. It's not really a tooth, but it tears apart meat. A pelican has a really big mouth so that it can scoop up fish in the water. Think of in Finding Nemo when that bird carries Dory and Nemo up to visit, or not Nemo, Dory and Marlin up to visit Nemo. He can hold like a whole big gulp of water and the two fish in his mouth. Then we have the hummingbird that has a little straw so that it can drink the nectar. And then the bird, or the duck, can
Good work! You've matched each bird to what its beak does. You've learned a lot about animal adaptations. Before we finish, let's take a quick look at the main points you covered. Adaptations are features that help animals survive in their habitats. In the model, you found that the large-mouthed creature was better adapted to the habitat with only healthy bugs. But the small-mouthed creature was better adapted to the habitat with both healthy and toxic bugs. Adaptations help animals do things like find and eat food, stay warm in cold weather, and keep safe. In the model, you found that mouth size was an adaptation for the creatures to find and eat food. Bird beaks are also adaptations. Different types of bird beaks help birds find and eat different types of food. Now that you've finished the lesson, click the lab report button to save or print it.
So if you did it on your own, you can click this lab report button and save it so that I can look at it later. Alright, and then go ahead and take the Lesson 5 quiz in your quiz packet. Once you're finished, if you want to look, there is a page in the book for it, but it might not help you that much, but you can look through section 4 also, because it also talks about the adaptations to help you with that quiz. And then you are finished with science for the day.